So far we've just been discussing the mathematics behind the physics and of waves and light and stuff like that. Right now I just kind of want to address how is this useful? Like, what's the point of all this? So one example that I can think of and come up with is how CDs are read. So, CDs are round and they look relatively flat, but on a microscopic level, they're actually not flat. They actually have small little grooves in them, indentations. If you look in the microscope, you'll see. So this is a CD right here, and these are sort of the grooves on the, I guess the flat portion. These are the grooves on the CD itself, the part that is red. And what happens is that when you place a CD into a CD player, you'll see that there's like a source of light or a beam. And what that beam does, that beam has a certain wavelength. So it shoots light, right? It shoots light up there, and then there's actually a detector. There's actually a detector, so let's just call that detector. Detector, and that's the beam. And it shoots light up, and keep in mind that the CD is rotating this way. So in other words, I guess it could be moving in this direction. And what that does, that beam will reflect back, and it will be detected by that detector. Now the next thing that happens is that obviously because it's moving in this direction, what I'm going to do is I'm just going to group all these together. Let's see if I can get those. Yes. And so that's the first one. Then what happens is that as the CD is moving, it's moving to the right, right? Now the beam will shoot out again, okay? And this time it will go like this. But this distance is actually about half a wavelength. Okay, and it'll come back here, and the detector will detect that, and it will know what the difference is between the wavelengths. Like, that's how sensitive it is. And so what happens is that when there's a difference between one groove or another, the detector records that as a 1. Okay, again, this is a CD player, and it's moving to the left, and then again, so let's just do this. This is the groove. I'm just going to replicate that. Right? So this difference here, is simply read by the, let me just do that. This difference here is read by the beams and the detector, and because there's a difference between a groove and a flat surface, that's a 1. Again, over here, there's a difference between a flat surface and a groove, so that will be read as a 1. Now, when the beam reads it from here to here, there's no difference, so that will be read as a 0. When there's a difference between this flat surface, between the groove and the flat surface over there, whenever there's a difference, it's recorded as 1. And then whenever there's a difference, it's recorded as 1. So as you can see, what this leads is this ends up being a string of 1s and 0s. In other words, this is the binary code that helps read the CD. So this string of 1s and 0s is then fed into an interpreter, and then that's interpreted into music. So by using wavelengths, by using that constructive and destructive interference, by knowing that difference, that's how all this sort of culminates into reading a CD. And also it goes into reading DVDs or Blu-ray discs. In fact, for Blu-rays, the reason why they're able to have like such higher capacity is because they have smaller wavelengths or larger wavelengths. So it's more frequent. They have more frequent, they can read it more frequently, and therefore they can read more data stored. And so that results in more 1s and 0s and better, sharper quality image because a Blu-ray disc can store more data. So that here is just a simple practical example of how a CD is read and why the wavelength of light is important.